demand system. The demand is created there to replace the ATP used here. All right. Sorry, it seems like silly, but those are the kind of preconceptions that you have to let go of in order to move forward. All right. So I'm going to talk a little bit about resting metabolism. If you just stay home and lay on a Barcalounger or lay in bed all day, do as little as you can, you're still going to consume, almost everyone in here is big enough to consume 2,000 calories. And, what are they doing? And we've talked a little bit about that. The resting metabolism is often called 1 MET. So METs are multiples of the resting metabolism. For those of you who are quantitative, 1/4 of a liter of oxygen per minute, or 3.5 milliliters of oxygen per kilogram of body weight per minute. These are typical rates of resting oxygen consumption. Almost all of this, or the majority of this, in the range of 70%, have to do with cellular level activities. Keeping the sodium out, the potassium in, very, very fundamental kind of non-visible, some people say, well, what about breathing? Doesn't breathing cost? Breathing's about 1% of resting metabolism. The heart's about 2%. So these sort of visible things that you would think were greatly expensive are tiny compared to the backdrop of just maintaining the cell. In the MPB lab class, don't you guys do a cell bath in one of the early labs and watch it consume oxygenation? Yeah, there you go. That's where most of resting metabolism comes from. Now it's interesting that if you just took this number, if I laid you in a Barcalounger and measured this, I would turn out to be low in terms of what you actually need in a day if you get up and walk around and move and dress and bathe and eat. So all the other fractions of this do relate to physical activity. The thermic effect of activity is the most direct one related to activity. It is just our cup of tea. And this accordion-style thing on the side is indicating that this could expand upward or collapse downward, depending on what the person did that day. It's the largest single variable. If I choose to run a half marathon today, I will have about 1,500 more calories that I need to consume in the next 24 to 48 hours. Right, so this is your biggest source of variability. We'll talk about the EPOC, the excess post-exercise oxygen consumption. This is what lay people call the afterburn, the oxygen consumption that takes place when the workout is finished. And I guarantee you that almost everybody overestimates how big this is. It's really quite small. I think one of you asked me at the very beginning of the course during an office hour, and I tried to dodge the question, does regular exercise increase the resting metabolic rate? It certainly does this. It creates a funny little addition, and then to the extent that you've added lean body tissue, it increases your daily maintenance cost because you have more muscle to retain. And then finally, for my UNA and other nutrition people, I think you all know, can I see how many calories were in this one? About 200? Yeah, it's just a great example. So UNA has just nourished herself, which we approve of. And if we read her dietary information, we discover that it's hard to find. If this is a 200-calorie snack, how many calories? Remember, she's chewed it, so her masseters were busy, and now she's going to secrete peptidases and other enzymes, and her gut's going to move around. What does all that cost? That's the energy to digest. It's about 10%. So 20 calories out of 200, whoever said that is exactly right. And we call that the thermic effect of feeding, which is basically saying it takes calories to absorb calories. We'll come back to resting metabolism later in the course, but for now, that's all you need. So how do we measure that? You get into this calorimetry. We think of calor in our language as calories, energy. Calor in Espanol is heat, right? And so calorimetry means literally the measurement of heat produced. And so there's two ways we do this in living animals. Animal scientists can do it too. You can do direct calorimetry or indirect calorimetry. The bottom line, the most important thing to know is if you do it right, the methods agree very closely. If you do them wrong, neither method works well. So in direct calorimetry, the great problem is you need a $3 million measurement device, which is basically a box, a small room, a cubicle, whose walls are made of copper piping through which water flows. So any heat, and then the outside of the wall is insulated to like R equals 100. Gigantically insulated from outside heat. So when that water warms up, it came from the body of whatever critter you put inside that box. Does that make sense? There's some real drawbacks to this, that it takes so long for the heat to come off the organism and go into the water that you can't really measure changes in metabolism from the first second of exercise to the 30th second. You can't do that. If you do an exercise bout, it has to be a workload the critter can sustain for more than half an hour to come even close to steady state. So these things, this is the gold standard, but there's a lot of things it won't give you. Because it's directly measuring heat, it won't give you information about what fuels the mitochondria are using, fat or carbohydrate. So let me talk a little bit about indirect calorimetry, because it's the trick. It's the one that I've used most of my life. It works great. I don't want to have anything to do with direct calorimetry. It won't answer the questions I'm interested in. So this is what you do in direct calorimetry. You've got a $3 million box. You measure the heat. Your subject, whatever they're doing, they have to do exactly that for half an hour to an hour continuously to get any data, and they cannot change what they're doing. The system is too slow. So what I would prefer to do is this. Measure oxygen consumption. Because we know the oxygen consumption is the source of the heat, the majority of the heat. And you then can actually, if you measure the carbon dioxide production, you'll see in a moment the logic of this. If you measure carbon dioxide production, you can actually deduce from the ratio of CO2 produced to oxygen consumed, you can actually deduce what fuel is being used in the mitochondria. So that's a huge people say, oh, if you're in shape, you burn more fat. Well, that's true, but you see how in order to say that, I'm sure Dr. Oz doesn't understand how that's measured. You measure the R value. And then the last thing is that this thing, you can do breath-by-breath measurement and watch oxygen consumption increase in response to a workload, which is what we're going to do for the rest of the lecture. So it has a whole bunch of power to do this indirect method. Okay. So, how on earth, you're going to find out that how on earth can we know simply by knowing? I remember, I'll tell you a brief story about why I went into this field. When I was when I was an undergraduate, I volunteered for a study in the Human Performance Lab here on campus. I just transferred from Santa Cruz. And I stood up to the treadmill and I had on the mask, or not the mask, the mouthpiece and nose clip, and I was getting ready to exercise. And the grad student was looking at my output on the computer, and she said, "You went to lunch about 2 hours before you came in here." I'm like, and she goes, "And you had a meal that was nearly all 90% carbohydrate." I have no idea how she knows this, right? What she's looking at is my expired gases, and she's telling me my behavior and food choices overlap to it's like, mystery witch woman. Anyway, so how does that work? It works because we already mentioned there's sort of stoichiometric relationships, the amount of energy in these simple macronutrients have fairly fixed values per gram, right? You can also, if you oxidize, take a gram of carbohydrate and burn it to ash, burn it to carbohydrate and water, or to water and CO2. There's also a stoichiometric relationship during oxidation, so that you can predict exactly how many kilocalories of heat you get out of fat per liter of oxygen. It's all part of the same stoichiometric relation. And so what this means is, if you know how many liters of oxygen were consumed, and can somehow figure out, well, it was 50% this and 50% that, it was 90% this and 10% that, you can actually figure out the fuel mix. So knowing these fuel-specific oxygen heat releases, you can figure this out. So we will now do some examples. So here's what I've done, just tons of. I don't particularly like this picture because it's not, well, it's okay. The subject is on a mouthpiece, nose is clipped. This, notice, is open to the open air. So when he inhales, the air comes into his chest. What we want is what he's getting rid of. We want his used air, because that will have more or less oxygen than what came in. Less, okay? We can actually, we can do an example. I'll show you the equation. So let's say he's inhaling 21% oxygen, which is room air. Room air is quite constant. This room is constant. So he inhales 21%. Let's say what comes out is 18 in the expired air. That gives you a, what, a 3% disappearance of oxygen? 3% of what? 3% of his total breathing. Let's say his total breathing was 12 liters per minute. 3/100ths of 12. I don't do that. Perfect. So it implies he has a pretty good lean mass, but that comes out to be 0.36 liters per minute, or 360 liters per minute. That would actually be a reasonable resting oxygen consumption for a Hussein-sized person. We need a big person with lots of muscle mass to get that big a resting consumption. The equation that I just used is this. V stands for volume, because these are measured in volumes. So dot over it means rate of change of volume, so this is liters per minute. The liters per minute of oxygen disappearance into the body is a function of the total breathing. This is volume of air expired. It's the flow through of that too. So this is the breathing, expired breathing per minute, times, this fraction is also often called the extraction fraction, where you're taking the difference in oxygen like we just took up here. Is that okay? So that gives us our total oxygen disappearance. Now this second equation down here, notice this is not rate of oxygen disappearance. This is the volume rate of CO2 appearing in the outgoing breath. Is that okay? And that, by knowing this, what we can do is actually get a ratio, which I think is where we're going. We could put CO2 divided by O2, and that defines, Manisha, did you guys measure that in your cell mix? Do you remember measuring carbon dioxide? That's a while ago. Has anyone done the NPP lab more recently with the cell bath, cell mixture? So the CO2, and this could be, as long as the units are the same, you could have it in whatever you want. This could be moles, it can be volumes, it can be atomic weight, I don't care. But CO2 over O2, and so remember, this is what's going into the mitochondria, this is what's coming out. Does that make any sense? So when we do this on a cell, or Barbara Horowitz, who has retired from the MPB department, spent her whole career doing mitochondrial homogeneity. She'd take a sample, bust up the cells, spin them, there'd be a little layer of brown, which represented the mitochondria. She'd pull that out, put it in one of those little cellular respirators, and measure, direct and personal, what the mitochondria themselves were doing. So she was one of the few people on the planet who were engaged in measuring what's called RQ, the respiratory quotient, all of the O2 disappearing into mitochondria and all of the CO2 produced are coming from mitochondrial respiration. The CO2 is broken off in the TCA cycle, and the oxygen disappears in the electron temperature. Is that okay? Now, if we measure at the mouth, we use a slightly different word to reflect the fact that there could be other things happening at the mouth. Let's say I just took a big hit off a CO2 cylinder, right? I could exhale and there would be strange things happening unrelated to my mitochondria. we call the same measurement, the same ratio, CO2 to VO2 at the mouth, is called the respiratory exchange ratio. You'll often hear people just call it the R value. And what that is, it's the exact same measurement, it's just you measure it at the mouth. Now, so long as the person, let's do the easiest one, the person is in rest and you haven't fed them a huge amount of food or poisoned them with strange chemicals, with metabolic blockers. At rest, the vast, all the oxygen is disappearing into the mitochondria. Nearly all. The some is being bound up in anabolic reactions, but it's tiny. And even more, 100% of the CO2 produced is coming from mitochondria. And so as long as the person is steady state, that would include rest, you can actually get a snapshot of what are the mitochondria doing in this body as a whole, simply by looking at the person's oxygen uptake in the mouth, which I find miraculous, and that's how my grad student knew I had eaten a carbohydrate-rich meal 2 hours before the exercise test. I'll show you that in a second. Everyone's tracking so far? So in exercise, this will also work as long as the person is in steady state. So as long as you're doing a workload that is below the anaerobic threshold and the person has sustained it for something like 3 to 5 minutes, so the oxygen consumption has stabilized, you get this same quality that what you're measuring at the mouth is so close to what's happening at the mitochondrial level that you can proceed. Is this all making sense? This is our, I'm spending time on it because this is our measurement entree into the life of the cell. There's no other way to do this. Okay, so what this means is for a given amount of oxygen consumption, you can deduce exactly how many calories of energy have been released or heat have been released. Watch. C16 is palmitic acid. Does that mean C18 is stearic? What is stearic acid? Is that C18? Anyway, so C16 appears to be palmitic acid. Remember, fats are highly reduced, and so you're going to have to add a lot more oxygen to them to get CO2 out of them before you can break the bond. And so if you look at this ratio for the complete biological combustion of fat, you get 0.7. You get 16 CO2s produced for 23 oxygens consumed. So make me a guess. One of the ways well, I'll finish and then you can tell me. Carbohydrate. Carbohydrate comes already fairly oxidized. So it takes less oxygen to reach an energy state that will break the carbon bonds. And as a result, you have a 1-to-1 ratio. For every molecule of oxygen consumed, a molecule of CO2 is made. So just taking these two numbers, how did if fat is our default, every morning you wake up and your R value is very close to this, that's the default fuel, if you haven't eaten anything in 12 hours, how did my grad student know that I had eaten a meal recently?
Your RER was probably like 0.8, 0.81.
Yeah, it was more like 0.95. So the first one was, it wasn't this, Moses says, it was higher, implying I'd eaten, which then your fuel mix moves to whatever the most recent meal was. It follows the available substrate. And then she knew, Moses, how did she know that it was carbohydrate that I ate? 0.95. My R value was like 0.95. And so I'd actually gone to Orange Hut, which is an old, I don't know if Orange Hut still exists, but it sold Chinese food, and I had a bowl of rice and vegetables. So I said, I got to get into this field. This is just too interesting. So, and then you can do mixes of these because the 100%, fasting greater than 12 hours or immediate post to sugar bomb, these are the extremes. But many of you had a thing we call it the morning meal breakfast. I had a bagel. And so you can go through, and by measuring the ratio of CO2 being produced and oxygen produced in that person at that instant, you can actually figure out, like if the RER, Moses, is 0.85, that happens to be perfectly balanced between the oxidation value for fat and the oxidation value for carbohydrate. And as a result, you get a 50-50 mix. If you see an RER of 0.85, the person is basically doing a 50-50 mix of carbohydrate and fats. So by being able to measure the oxygen consumption with the CO2 production, you can, and measuring it closely in a steady state, you can actually discover the total amount of energy that the mitochondria are releasing and the fuel they're using to do that. Yes, sir? What if you just ate protein? You deaminate, so protein, remember, is an amino acid polypeptide. It's a chain of amino acids. And amino acids are carboxylic acids on one end. I can't make a carboxylic acid. And they are amine groups on the other end. The short story is you cleave the deaminases, cleave this off and throw it in your urine as urea. Two amine groups make a urea. And you've got a carbon chain that is a carboxylic acid. So protein is carbohydrate to the body, unless it has protein synthetic needs. All right. Oh, and Drew's question is, because yeah, I'm doing a very simple sort of binary, dichotomous, that either the mitochondria use fat or carbohydrate. Couldn't it use protein? It won't usually use protein. Protein for catabolism, especially during exercise, is avoided. The other secret is, Drew, if you take apart, it took me years to figure out why we ignored it, so we call this oh God, I've lost it, protein excluded equivalence. We exclude protein as a fuel because, number one, the body doesn't want to use protein as a fuel. But the second one is, if you actually take apart several kind of average proteins, collagen, hemoglobin, blah, blah, their R value turns out to be exactly this, meaning they don't influence the at-the-mouth breathing. So usually proteins are far less than 5% of the metabolic mixture, unless you've done something very strange. Is everyone okay so far? Okay, just to check. So we're going to actually start to look at, we're going to deliver some workloads and watch the body respond. Oh yeah, that's very good. So we've already said that energy, ATP metabolism, you have overlapping series of ATP resynthesis. We're going to see as we go into exercise that metabolic responses are the consequence of you activate a certain amount of muscle, and that muscle is reliably consuming ATP at a certain rate. Well, then your resynthesis becomes very much limited on how quickly the muscle's consuming it. You have to use the pathway that can replace it as fast. Right? The other issue is, which particular motor units have you recruited? Are they oxygen using? Are they lactate producers? Have you undergone a training conditioning that has shifted their metabolic preferences? Those are the two things that create metabolism. So realize that metabolic adjustments are not predetermined. The brain has nothing to do with metabolism in terms of pre-spin. We are working at 50% VO2 max. Please engage the mitochondria act. They do not have, the brain does not have that dial. What the brain does, it recruits the amount of muscle and the amount of force you need to get it done. And then what happens at the cellular level is metabolism catches up. It's a response. Does this make sense? We are not in control of our metabolism. At least in the way that people on the internet seem to talk about. So there's a question on our midterm. We said, true or false, the rate of ATP regeneration at VO2 max is the highest rate of ATP regeneration possible. And that's false, because if you look at this, VO2 max would be that's oxidative replenishment of ATP. And notice that every other of the four other mechanisms we talked about, anaerobic glycolysis, creatine phosphate, and ATP, so the three other mechanisms all have higher rates. So you could go back to slide 16, lecture 8, and look at this table, the rate of ATP resynthesis, and discover if you take a weighted mean here of the two mitochondrial sources, you might get 2. We'll make it heavier, 2.5 millimoles of ATP per kilogram from aerobic sources, well, every other thing on the chart is at least double that. So, oh, you can replace ATP much faster than VO2 max. You just can't do it for very long. Okay, so now into the guts of the lecture with, this is the important part. So this is real oxygen consumption. This is an idealized figure, but I have measured this thousands of times. This is oxygen consumption at the mouth. The workload started right there. Resting oxygen consumption, let's see, in these units would be right there. So they start pedaling, up comes, and the point is that this looks to be, for whatever this workload is, that looks like the oxygen consumption required to do the work. 25 mils per kilogram per minute, that's about 40% for you guys, that's about a heart rate of 100. It's very light workload. Notice though that the mitochondria, remember I kept telling you that mitochondria take time to catch up? You know, how do I know that? Somewhere between 2 and 3 minutes for this light workload, the mitochondria come up from their resting value through allosteric activations and finally reestablish a new metabolic steady state and heterostasis, allostasis, that copes with this workload. That make sense? So the first thing to realize is oxygen uptake is always a following function. Nobody knows in advance. The brain doesn't know what the oxygen consumption is going to be. The brain knows you need to get away from the tiger. The cells are in charge of catching up in oxygen consumption. Final steady state takes 2 to 3 minutes. Oh, and the amount of time it takes for your mitochondria to catch up depends on how hard the workload is relative to your abilities. So this is a harder, notice they've changed the time scale down here. This is a much harder workload. We said if that's 25, this is 50. Oh, this is 2 times as hard. This is approaching 80 to 90% VO2 max, even if you're in shade. And so what you're seeing is you're probably not getting close to a plateau until 5 or 10 minutes. And then it looks like for this particular person, as the work goes well beyond, some additional sources of energy consumption are coming up late in the work. So even at this very high workload, apparently the steady state rule will only work for the first hour. And then things start to fall apart. Am I making sense so far? So you get these ideas. Okay, next question. It's a good question. So we said the workload started here, but the oxygen consumption didn't reach the energy demand of the work till 3 minutes. So explain to me, how was the work getting done in the first 30 seconds? Because it was. I was watching their feet turn the pedals. You can say that out loud. Yeah, something that doesn't have to do with oxygen consumption, anaerobic. You start to see, oh, of course, that's why we have this anaerobic reserve of creatine phosphate and ATP and the cytosolic production of energy. It covers the start of exercise, among other things. And so there's actual word for that. This is theoretical. This is showing you that would be the total energy cost, and with the onset of exercise, your rate of ATP synthesis has to be that. The problem is your mitochondria can't do that. So what do? Something else that doesn't require mitochondria. And there's a word for that. We call that the oxygen deficit. So the difference between the energy requirement of the workload and the actual instantaneous oxygen consumption at the onset of work in the early minutes, that difference is called the oxygen deficit. It's what you couldn't come up with at the start of the work. Yes, Mary?
Is that why you start sweating a lot after you start warming up?
I'll talk more about sweating response, but it is also true. Heat buildup is most intense at the beginning because heat buildup, when did heat buildup start? Heat buildup started right there. When does heat shedding start? It usually takes about 5 to 10 minutes, and so you usually notice you can actually use an equivalent concept called the thermal deficit, that in the early minutes of exercise you're storing tons of heat, and at some point you need to dump it. Anyone here a swimmer? Oh, where's my Dallas? Oh, it's Stephanie too. You ever notice how when you first get in the pool and you do like the first lap, you almost don't have to breathe. You know, you're doing the first lap and it's like, I guess I'll breathe every, I don't know, fifth. I really didn't need to do that, right? And then you keep swimming, you get to the fifth or sixth length. Suddenly you're breathing every other, right? That's what it is. In the early phase, you're not tapping into oxygen-based work, you're not making a lot of CO2, and so it's kind of irrelevant whether you breathe or not. Many 100-meter runners, you guys know 100 meters? People run 100 meters. They don't breathe during the race, or they take one breath. Why would they need to breathe? All the energy is being produced from non-oxidative source. All right, so that's the oxygen deficit. A couple of things about it that are illustrated here. The difference in the energy requirement of the exercise, versus the actual oxygen consumption at the onset of exercise. Notice that when the workload is small, this would be about 40% of VO2 max. It looks like we're 50, so a heart rate of about 120 for you guys. Notice that at the end of exercise, you don't instantly drop back to resting metabolism, just like there was a taper on for the mitochondria. There is a taper off in the oxygen consumption. Notice too, this figure is not as good, but when the total oxygen deficit is small, this thing is small too, which we don't have a name for yet. We will in the next slide. The bigger the energy requirement at the onset, this workload is nasty. This is 110% of VO2 max, 130% VO2 max. Horrible thing to do to someone. I can guarantee you how long this time is. I've never met anyone who can do this for more than 4 minutes. So this is a miler trying to pop out 4-minute mile. Notice their mitochondria actually get to near maximum by 2 minutes. The problem is the workload is actually higher, and so they are constantly using not only their maximal oxygen consumption, but a top burner, an overdrive of anaerobic energy consumption, which is why they're such bad walkers when they finish their 4-minute mile. You see them they have really topped out all their energy demands. Yeah?
A couple slides ago, you said that the time to plateau is proportional to the total workload.
Yes.
So wouldn't it have taken longer?
Yeah, it really should. The way they drew that picture, thank you. Where was that? I don't do that. Hang on, Moses. Can we use this one instead? So put a line through the figure I just showed you. This is just a better set of figures.
Okay.
It's hard to find good figures. Everyone makes these idealized graphs. I would rather go down to my lab and actually make the graphs. So what we call this follow-up tail is called the EPOC, and that's a complex acronym. The excess over rest, post-exercise oxygen consumption. It's what beginners used to call, we called it the oxygen deficit back in the oxygen debt. We don't call it the oxygen debt anymore. And you'll see why. It has to do with the... So EPOC is the recovery. This is the deficit. So here's a better one, Moses. Here's a really light workload, 20% VO2 max, heart rate of 80. There's the oxygen deficit, and that would probably be less than 2 minutes. Here is the EPOC, or post-exercise oxygen consumption, what lay people call the afterburn. And notice it also is done in less than 2 minutes. Again, I'm going to bleed to death in the gym, biting my tongue. I hear the trainers going, yeah, the best thing is that when you finish this workout, for hours afterwards, you're burning more calories. You're burning 1,000 calories. No, you're not. Most epochs, a big epoch would be 15 minutes. If it's the routine exercise you usually do, you're probably back to baseline in 10 minutes. Sir?
Why do a lot of trainers say that you do interval training, your metabolism is stronger after the workout, and you burn more calories?
Talk to me in office hours. Again, you will get a bigger epoch if you do. That's what they're saying is if you do high intensity, well, let's finish. So here's this, light work. Now here's a workload that's like 80% of VO2 max. Notice that the time, because that looks like in this figure they did keep the time the same. The x-axis has the same units of time. And notice that this did take longer to get to, maybe 5 or 10 minutes, Moses, which was your point on the last one. And then let's see if they did the same here. Again, people never think about, again, they think they're pretty cartoons. They don't realize they have meaning in them. So down here is a super maximal workload. And notice that, yeah, this should take longer to get to maximum than this. And people just don't draw it very well. And then the answer to your question is, if you're doing interval work properly, where you're really hammering it, you might go above VO2 max. Notice that this does indeed increase the size of the epoch, which does increase your afterburn. But again, it's not thousands of calories in hours. It's tens of calories in minutes. It's just people are always incredibly optimistic about this whole thing, and they make you promises that are far bigger than what you're actually doing. Nothing wrong with interval exercise. I hope to do some today. Oh, we're almost out of time. Does this all make sense? By the way, notice that when you have an offset in small workloads, oxygen deficit and epoch will almost be equal. The harder the workload, the more the epoch grows. The epoch is always bigger than the deficit. It can't be the other way around. And the harder the workload, the greater the epoch grows in relation to the deficit. Is that all okay? So the reason we call it epoch and not oxygen debt is A.V. Hill in 1917 thought that excess oxygen consumption after work, this is the only Nobel Prize given for exercise physiology in the last 100 years. Maybe I'll get the next one. No. He thought that the lactic acid that was still in the bloodstream was being resynthesized, which would cost oxygen, into glucose. And so the reason we abandoned the word oxygen debt is because he said that was why it was happening. And when you actually label and measure the lactate after exercise, that's not what happens to it. The body uses the lactate as a pre-digested fuel. And then if you need sugar, you go find some sugar. You go eat something. So the way that we replace glucose is... End of class. You can read that on your own. We'll talk more about where the epoch comes from next time.